Hey everyone. Alright, so we're going to talk just for a second here about trigonometric identities. There are a number of fundamental identities. An identity is just a fancy word for an equivalence. Two things that are equal to each other. And we can use these basic identities, these fundamental identities, to prove other more complex equations, more complex identities, and we can actually use them to solve problems if we wish. So let's take a look at some fundamental identities that we can use later on in our discussion of trigonometry. The first six you should know already, and that's kind of nice. These are called the reciprocal. Oops. Let's try that again. All right, here we go. The reciprocal identities. These you already know, I hope. What's secant? 1 over cosine. It's the reciprocal, isn't it? What's cosecant? 1 over sine. Right? What's cotan? 1 over tan. But guess what? We can flip those around, can't we? If I told you that 1/2 was the reciprocal of 2, wouldn't you tell me that 2 was the reciprocal of 1/2? Doesn't it work the other way too? If 1/2 is the reciprocal of 2, then 2 is the reciprocal of 1/2. Well, it's true here too, right? If secant is the reciprocal of cosine, then cosine must be the reciprocal of secant. Sine is the reciprocal of cosecant, and tan is the reciprocal of cotan. So we have 6 reciprocal identities. The next two are sometimes called the quotient identities, and they deal with tangent and cotangent. Remember we said that when we talked about the unit circle that tangent was y over x, was the y coordinate over the x coordinate, right? But what is the y coordinate? Isn't the y coordinate our sine value? Y over, and our x value is the cosine value. So tan can actually be equal to sine over cosine. And since cotan is the reciprocal of that, can't we say that cotan is cosine over sine? Sure we can. So there's 2 quotient identities that we can use. All right? Your last ones are a little trickier. These are called, although the name is not that important, the Pythagorean Identities. And the reason they're called the Pythagorean Identities is because we can derive them from, and they look an awful lot like the Pythagorean Theorem. Okay? So let's say we're on the unit circle. This one needs a little bit of explaining. Let's say I'm on the unit circle. Okay? Where's my unit circle? Here's my point. And there's a right triangle. Remember, this is how we came up with the unit circle coordinates. And the unit circle had a radius of 1. Okay? My x value was what? My x value was my cosine. And my y value, draw an arrow here, was my sine. Could have drawn that a little bigger. You know what? Let me make it a little bigger. Let's draw a bigger one over here. There's my right triangle. Okay? Point on the unit circle. So it has a radius of 1. We have our x value, which is our cosine, and our sine is our y value. What does the Pythagorean Theorem say? Doesn't the Pythagorean Theorem say a squared plus b squared equals c squared? If I square one leg and square the other leg, add them together, I get the square of the hypotenuse. Well, look at this right triangle right here. So if I take the sine and square it, and add the cosine and square it, I get the square of the hypotenuse, which is 1 squared. Now, before we go any farther, You've got to learn some new symbols here. They're not actually new symbols, but there's a new way of writing the square for trig functions. It's a very specific way to write it. When you want to write this, you put the square after the sign. When you write cosine squared, you write it there. That is just the way we write this. So, if we want to write this, you must write this. Okay? It prevents unclear ways of writing things. That could look like the sine of the angle squared. And if that's not what we mean to square the sine of the angle, you're either going to have to put it in parentheses, or we can prevent using parentheses all over the place and put the square in the middle of the function. So that's how we write square. So we can do it with any trig function. If we want to talk about the square, the tangent of theta squared, tan squared theta, we could even use higher powers. Cosecant of theta cubed, which would be the same thing as this. Okay, so that's the way it's written, equals 1. 1 squared is 1. There's my first Pythagorean identity. Pretty important, and we'll use it later on when we prove some other identities. Okay, there are two more Pythagorean identities, and they're derived from this one. The first one is derived from your basic Pythagorean identity by dividing everything through by sine squared theta. You can do that. You should know that. As long as you divide everything in an equation by the same number, you're okay. Alright, so what happens? Sine squared theta over sine squared theta is 1, isn't it? Cosine squared theta over cosine squared theta, let me rewrite this, is cosine theta over sine theta times cosine theta over sine theta, isn't it? Don't you get cosine times cosine is cosine squared, sine times sine is sine squared. But if you look back, not too long ago, we talked about cosine over sine, didn't we? It's right here. That's cotan. So that means we can say that this is, oops, let me get rid of that. This is cotan times cotan, or cotan squared theta. And this is 1 over sine theta squared. The reciprocal of sine theta squared would be cosecant squared theta. There's my second one. And then my last one, divide everything through from my fundamental, my basic Pythagorean identity. Sine squared theta plus cosine squared theta equals 1. Divide everything through by cosine squared theta. So we have some similar construction here. We always write this one first, which is my 1 plus. So what's this? Just like we did here, we can say this is sine over cosine times sine over cosine. But sine over cosine is tan. So that's tan squared theta equals, and 1 over cosine is secant, but we've got 1 over cosine times 1 over cosine, or secant squared theta. So those are my 3 Pythagorean identities. I hope you notice that you really only have to look at one of those, memorize one of those, because they have the same form, and you'll notice that, just to help you remember it, that the co goes with the co. The cotangent goes with the cosecant. And the two that don't have co's on them, no co, go together. Okay? Those are your fundamental identities. You'll be seeing them again. Commit them to memory. See ya.